Okay, hopefully this is not, all right. I was talking about managing expectations, but this is much more about using methods like, say, coming from system dynamics, coming from mathematical epidemiology. I would like to accentuate that I'm actually, methodologically speaking, I want to discuss when we have this kind of problems, what we do. I do not think data science and statistics are adequate enough for doing this kind of modeling. I'm going to be discussing a few, several, actually quite a lot of examples. In the beginning of this presentation, because it's a fairly eclectic group as far as we can tell, I'm going to be as visual, use as many visual aids as possible. The technical part is going to be pushed after, say, the first half an hour. Ideally, I can give an overview, which is going to happen, say, within the first 5-10 minutes. And if you decide that the rest is too technical, you can do something else. So I have implemented this both in Mathematica and R, the algorithms I'm going to show. Mathematica is very similar to R. And basically, if you're please, there's some background noise, and I'm sorry to sound negative, but it's very disrupting. So
it looks like everyone's muted, so I'm trying to find who's
the culprit.
The noise.
Yeah.
There you go.
Right. So if you're good in programming in Mathematica, you can become a relatively quickly good R programmer, and the other way around. I have been using Mathematica for 25 years. I've been using R for like 6-7 years. The first examples, I'm sorry, this is a little bit too much hand waving. So let's actually bring some examples here. So this is just as a warm up, what we're discussing. What is the thing? I'm going to bring up some data from New York Times. They have a GitHub repository in which this data is it can be retrieved. I mean, you can see I'm directly taking it from GitHub. So there's so basically this can show you some kind of state of the propagation of that disease in US. I'm going to explain a little bit more what this disease is if you don't know about it, or what are the assumptions, at least for this modeling endeavor I'm going to be describing. There are several ways to describe, to plot this, and this is actually an HTML. So let me see, I think I have a live notebook somewhere here. I'm going to bring it up. Maybe it's going to be more informative, or just more interesting, or not, from what I can see. Okay. So yeah, I mean, we can see what, say, from the counties data I have been like we have the typical Pareto principle adherence. We basically can see here, for example, 10% of all infected cases correspond to close to 90% of 10% of the counties correspond to 90% of all infected cases. And so similarly, a very similar statistic is for the deaths. And the distribution here, across US, you can see I have cut out Alaska and Hawaii. I mean, if you want to see Alaska and Hawaii, you can see them here. Okay, or whatever leaflet is doing. There are some other ways to visualize this. Another approach is to look into the time series, the aggregated time series of the different cases and deaths. And this is here, it's a logarithmic plot. You can see what, say, it's actually not growing, it's actually start to get flattening. So whatever it is being done right now, politics-wise or policy-wise, it's being, I guess it's working. All right, so this is just as a warm-up. If this is not this kind of prediction and forecast, this is not what I'm trying to do, not what I'm going to talk about. If this is your, I don't know, if this is how you address this problem, that's simply not adequate. It's borderline pathetic. So now with this statement, you might hear stuff which, I don't know, you might not like. I guarantee you that most of my current and former employers wouldn't like to hear everything I'm going to say, but I really hope that, you know, being a little bit more frank or more cynical is going to bring point. All right, so I'm going to be discussing the patient 0 over USA example, which actually, interestingly enough, disappeared from my screen. So I'm going to retrieve it again. And as I mentioned, this is probably this is the interesting part here. Sorry, apologize. This is it. So what we're going to see here, this is propagation. Okay, I cannot zoom it, I guess. This simulation here shows how patient 0 is, you know, starting somewhere from Seattle, how patient 0 can propagate the infection throughout USA, and also summarizes some of the effects of what is happening if we take different quarantine scenarios starting at different points. You can see the famous flattening of the curve here. One of the, in order to make this this plot here, actually I made the quarantine indefinite, and it is from this plot it can be seen, but there is the right time to do this. There is a, you know, you cannot actually, I mean, doing it too late, it's also it's not going to bring the desired effect. Like say no quarantine and T 100 days, right? I mean, they're basically very close. If you look into this animation again, you know, when it cycles through, there is going to be a patient 0 arriving somewhere here, as I said, in Seattle. If you look closely to this in the background, what is happening, there basically some let me just bring it up, make it more obvious. So I'm using this part of I'm basically having different partitioned USA in some ways, and so I've been taken some of the airports, the most popular airports, and I've plotted the traveling patterns between the different site locations in US. All right, so to some, I mean, as I mentioned, this is probably the most interesting part of the talk. The rest is what I'm going to be describing how I've been doing this kind of simulations and what kind of implementations I have done. So with this, there's a big picture here when we discuss this kind of modeling. And let me bring the big picture here. So we observe something like COVID-19 happens, right? We observe the phenomena. We want to say do some modeling. We want to do some policies and do certain. We're basically trying to figure out what to do. So we gather relevant data contextually, contextual about, say, the disease, like say number of hospital beds per state, or number of hospital beds per city or county, some other data, demographics and etc. Massage the data and start making models. Obviously, different type of models can be done. The data analysis is very important. You know, like say whatever kind of measurements I showed from New York Times data, like how faithful they are, how good they are, or how representative they are to reality, that's not a trivial question. And anyway, so we basically, we do need to, when we build this kind of models, we need to be discussing it with the others to observe the data. And to some extent, what is happening with this presentation, what I'm doing something related to that. Building the models themselves, that's great, but we should attempt calibration. We might not attempt calibration immediately. With the models we have developed, we can do some kind of qualitative simulations. This animation I showed earlier was exactly that. It was patient 0 simulation through, I mean, I used realistic traveling patterns through the airports of US, but everything else, you know, was basically just one patient and you know what kind of I put certain numbers about the contact numbers for the disease and so forth, right? And I made a scenario play out, and then actually this kind of shows how the whole thing propagated, aggregated the number of infected people, and simulated some quarantines. So basically, all this I did without much too much data, in a sense. Like I only knew what are the populations at the different locations in US, and when I say only, that's actually quite a lot of data preparation for that is needed, and the traveling patterns. So at some point, we do need to calibrate the models, especially if you want to do actionable type of advice. And so there's a particular when we basically calibrate the models, this can tell us how good are we with how adequate are we with our approach. So obviously, I'm not thinking about one model here. There can be multiple models. We do bulk simulations. We collect the experimental results, do the corresponding visualizations and dashboarding, and bring it to the decision makers. Model calibration, again, can be quite hard. So we do actually need to solicit opinions both from team members and stakeholders. I'm going to return to this big picture again, I guess, at some point. But yeah, this is actually a very, it's an important, let me see. This is supposed to be a live link, which surprisingly doesn't, when I click on it, does not want to react to it. All right. Hey, well, no, I need to, that's not good enough. Hey, well, whatever. Okay, so the overview from the modeling perspective, there are actually several, and I'm going to bring this here. I'm going to, this was what this link was supposed to bring up. And actually, that's probably not bad that I'm going here. So I'm very interested in system modeling. And so I started a particular project, the coronavirus propagation dynamics project here. And what I wanted to show was, I mean, you can see some of the elements we discussed. It's one of the documents here, which I'm trying to find out where it is. And this is the coronavirus propagation modeling considerations. So there, from the more important part is that we do actually, from the modeling perspective, is that we have two types of populations, the ones which are severely infected by it, and the ones which are normally symptomatic and severely symptomatic. Now, some people say there are four. We have like critical, severely symptomatic, normally symptomatic, and asymptomatic. Sure. In the modeling, I'm going to be considering, I'm separating this just into two, and this is in order to advance with the modeling activity and perspectives. But around this breakdown, but around 20% of the people have become severely symptomatic. I mean, it is baked into the models I'm going to be doing. The other is that there's some estimates about the incubation period and the infectious period. You know, in this part, when you do standard compartmental models, you know, the infectious period in some of these models is being skipped. I'm not going to dwell too much on this. I assume this is, to some extent, this is already sufficient for me to start modeling. And I do actually want to bring a couple of points. One of them is organizational. So every 5-10 minutes, like now, I'm going to stop and answer some questions. Basically, the stops, they're going to be more or less conceptually separated from, you know, conceptually marked, you know, from the different parts of this presentation. So the other is that there's several ways to model this kind of, to produce this kind of models we're talking about for epidemics. I'm using a classical model predominantly. This is a classical equation-based modeling. There's also agent-based modeling, and if someone is interested, you know, they can do several automata. Several automata has been applied. not most recently, but they're like these three paradigms which have a place for modeling this type of situations we have. Now, I do actually want to mention something else here about the scope, about this, and I cannot apparently rely on my mind map to get the thing shown, and I'm going to try to make one more attempt, and I apologize. I thought I was more organized about this. So this is it, I guess. Yeah, okay. So when we discuss modeling of in epidemiology, there is the micro scale, the mesoscale, and the macro scale, obviously. Macro scale and geographical scale, they're kind of, obviously the same. I am not dealing with the micro scale. I'm dealing in this presentation. I'm dealing with mesoscale and trying to move mesoscale into macro scale. All right, so I'm going to look into some questions here. And so Will Hunter, does your model assume 100 quarantine policy being followed? Yes and no. And I'm going to explain that. Basically, when I plug in the quarantine scenario, I basically try to figure out there's a coefficient with which, say, the contact numbers are being decreased. You can actually increase them. And this is what is happening, say, in Florida. It's supposed to be a lockdown, but people went to the beaches and basically, kind of increased it was negative effect. Another question from, let me see. Don Jackson, what about the genetic analysis showing that there are multiple index patients see next strain? Sure. Right, that's a very good question. There's some fundamental assumptions when I make this type of models. One of them is that, okay, the virus doesn't change. If I want the virus to change, actually, with the paradigm I'm going to present, which is this multi-site extension, the same type of thing can be done with using different strains or different, mutations of the virus itself. And what role do you think the following two variables, this is from James, what role do you think the following two variables play in propagation? Population density, proportional use of public transportation, such as subways? Yes, very, very good question. This is actually one of the things I'm going to be discussing somewhere here. I mean, I can probably, I don't know, let me see. This actually, since somebody has brought it up, maybe I can actually answer this question fairly quickly. Let me see, do I have the prepared part here? And if I do, I'm just going to, well, I'm going to answer it. And I apologize, let me see again, like, yeah, all right, so, well, here, no, yeah, this is actually related, but you cannot see the effect of the patterns and the traveling. There is another one though, which I'm going to be showing. Actually, this is one of the things I'm going to be showing. It's this kind of question about the two variables being. It's very good to be answered on, say, some like, say, regular grids, not like, say, like some general grid, like, say, US or some kind of real life. But you can see in some kind of regular grid, I can actually try to see what are the effects, and say one of the expected effects is to produce some sort of wave of the disease going through the graph, and this is what I see. So yes, I mean, I can answer exactly this kind of questions. In order, first of all, I need to build confidence in my models, right? And so I need to ask myself about this. I can do this in several, about the effect of the variables. I can do this in several ways. One is to something called sensitivity analysis. The other is that obviously I can make this simplified test cases in which I can see that the models produce the results which I expected. That's actually required anyway in order to know that I'm actually on the right path when it comes to modeling. All right, so I'm going to continue with the modeling consideration part, which is with the next part here. And what is exactly, I mean, what exactly is kind of a warm up about why we model this in this way. So I'm going to bring a notebook from, I guess, wait for some notebook here, just a moment. Yeah, I mean, I thought I can rely on this mind map tool to click on the different links and get get the materials presented, but I guess it's not happening. So, all right. So what we see here is that in the classical compartmental models, and I'm talking about this part here, right? Equation-based modeling. So it's like we assume that we're in some kind of big village or like a university campus. Like there's like, say, one grocery store, one library, one bus or something. You know, it's like everyone is meeting everyone and is getting in touch with everyone. If someone is infected, other people would touch the things this person has been touching and so forth, right? So in some sense, we have this kind of complete graph. But it's very easy to imagine that it might happen that we don't have this. I mean, we have some kind of, like, even say cities like, say, Orlando or Boston. You know, there's certain typical patterns of where people go, typical patterns between interaction of people and you know, different neighborhoods, and also based on a certain occupation or demographics or whatever. I mean, we actually don't have this kind of complete graph. It's actually much more separated. And unfortunately, I cannot actually with, this is a great package here called iGraph, which I'm using for visualizing this. I do also have some other visualization, which I think in this particular case is going to be more helpful. And this is where I'm using some kind of social networking type of yeah, the complete graph. But imagine you have this kind of graph of interacting between the people. And so after I kind of try to cluster the nodes of this graph, I'm kind of getting this kind of cluster here. And so with this cluster, you know, I mean, it is then the classical models, they're more likely to be applicable in each of these clusters separately, but not all together for the whole site or for the whole city. And so this, let me see, maybe I can do this easily, like, say, just made some random graph here, I guess. So what's Strogat's graph distribution? It's about so-called small world modeling. And this here, I mean, this basically shows how I can basically propagate the virus through the network. And I started with some nodes, which was somewhere here, right? And so obviously, if I start with some node somewhere here in the middle, you know, like this kind of propagation might happen much faster. What I'm showing here, it's actually not, this is just a rationale, this is just a warm-up for discussing compartmental models. It's actually, it's much closer to what the so-called agent-based modeling is doing. If you're more into, say, I don't know, if you prefer more statistical methods or machine learning, actually machine learning before the neural networks revolution happened was much more about what agent-based modeling is doing. So it's much more ad hoc. It allows certain scenarios to be played out, which are very difficult to catch with with the modeling techniques, which I'm going to describe next. And so the modeling technique which I'm going to describe next is called system dynamics. So this is here. I actually, this time this worked. If you're interested in system dynamics, there's this is actually a theory which was done developed in MIT. And one of the reasons when I initially started discussing with Rachel, having this presentation, is that, yeah, I mean, actually, I do think it kind of needs to go in that place, in that city, in that place where this technique started. System dynamics, it can be shown and demonstrated in several ways. I'm going to switch to another screen here where I can do my my demonstration with this. with a tool called System Modeler. So System Modeler uses a language called Modelica. Modelica is an open source object-oriented language. It is there's organization, but you know, like let me see. So Wikipedia should have an entry, right? Yeah, maybe, right? And so we can. It's very convenient to specify systems of differential equations. Now, system dynamics. Since I'm here in Wikipedia, system dynamics is a way of doing, yeah, misspelled. And it's a way of modeling dynamic systems with a relatively simple set of concepts, I would say, where basically stocks, flows, rates, and you know, feedback loops. So I'm going to be using this. Now, this actually, system dynamics, overlaps fairly nicely with mathematical epidemiology, the classical mathematical epidemiology, which has been, I guess, in development for the last 90 years. So, all right, and so now what I'm going to do, I'm going to show the system modeler, which implements this package here in system modeler called system dynamics. System modeler is gives an implementation of Modelica. So Modelica is like, say, HTML, and you have different HTML rendering engines. So similarly, you have Modelica and you have different implementations of Modelica. Like some of them are paid, some of them are open source, some of them are like, they have some other restrictions being used. With system dynamics, as I said, what we are going to be look at is, it's basically, we have bathtubs, right? Some sort of simple concept like that. These are valves. I'm going to be discussing something I hope everyone in this, participating in this presentation, this meetup is familiar. So we're basically trying to see what is the effect of discovering bugs and software bugs, and this discovery of software bugs accumulates them in some way. Obviously, they need to be fixed. And so what is the dynamic between the fixing of the bugs and the accumulation? The way that these software bugs are accumulated, you can see I have put here a certain pulse function. This means that imagine you have something like Agile or Scrum, and this kind of management paradigms for developing software. And so imagine your sprint in this Agile development is 2 weeks, and the first week the programmers develop, the second week the testers find bugs in the software they have developed. So more or less this pulse function here, what you see, it's that. It's basically you specify what is exactly the rate of finding, what is the background of finding bugs, and what, you know, when this week kicks in, the testing week kicks in, how much bugs are expected and so forth to be discovered and so forth. Now, I want to simulate this. So I'm going to press a simulation button, right? This is going to start a simulator for this. And actually, let me see. All right, so this actually, I need to, I guess, make sure a fair amount of this being plotted. So the most important one, I don't see it here, so it's this one. So yeah, we can see here that with this, if you look at, if I go back to here, so whatever kind of bugs finding is happening, there's a fixing ratio with 1/6, like around 17%, right? So this is the delay I'm talking about. And so this, again, like this picture, what we see, we have some sort of valve. This valve, it's controlled by some kind of throughput, think water, throughput or water flow of bugs. They're being accumulated in this bathtub. You know, this is the software with bugs. Now, this in general, this is supposed to go here, but that's valve which controls that. It's being controlled with this ratio, which tells me how quickly the software bugs found in this, which are in this bathtub, how quickly they're going to go through this valve. And you know, do something else after that. So I'm simulating this right now, and you can see that this orange curve, this is the accumulated bugs, this is hopeless. And so this is the software to be reworked. And so I'm going to change maybe some of the parameters here, and I'm going to see, do I get better results? Like say, if it is say 70% instead of 16, I need to rerun this. It looks more manageable. Or even if I tell my programs, no, do actually fix 87% at least of the bugs, you know, then you can see what, yeah, starts to look in a manageable type of more manageable the amount of bugs, and you know, generally the life with it kind of goes to some sort of equilibrium. What is interesting here though is that the bugs were found with this pulse function, but they evolution and accumulation, it's actually having this kind of wave, you know. So this kind of non-linear effects which are happening in relatively simple systems and relationships. This is actually one of the reasons system dynamics is being created and is used. This, what you see here, all this there's some differential equations being solved in the background. This is what Modelica is doing. As I mentioned, we're using a language to specify systems of differential equations and, you know, solve the models. So, but you don't need to know differential equations here. It's actually fairly simple. I can very easily explain this to stakeholders first. I can also ask people with domain knowledge to actually design diagrams like this and produce certain simulations. All right, so I'm no longer going to be talking about the system model, and so I'm going to be returning to the other parts of the presentation. Let me look for some questions here.
And if it helps, I can read the questions too. So
yeah, I'm sorry. I see only one new question. Mm-hmm.
Okay, so there's just one there. How else have you used iGraph?
All right, iGraph is it's fairly impressive in many ways. I haven't used it as much as I want to. If I do actually use probably like say at least 50% in my work time. And so when I'm using in my opinion, I have no choice. I'm using basically iGraph. So now the thing is that very often for the type of work I'm doing, like say I do quite a lot of recommendation systems and some sort of time series analysis and again, recommendation systems, so search engines for time series and so forth. Graphs, they are probably a way to visualize things, but they're not necessarily operational. I mean, I'm always going to be immediately going to the matrix representation of the graphs. And so I wouldn't be using graphs as much. All right, so I'm going to, Rachel, how long is going to be this lecture? It's already 45 minutes. I guess it's 1 hour and a half. I have already also at least 45 minutes more.
I had it running until 7:30, correct?
Perfect. All right, great. So now we're going to, I mean, let's talk about, you know, hospital models and whatnot. I mean, like, yeah, compartmental models, yeah, hospital models too, but epidemiological models. And I'm going to try to convince you that this this type of modeling approach has something to do with, I mean, it has a lot to do with it. First, though, we need to discuss exactly how is this, what exactly we model, right? And so here, as I mentioned from the overview, I have I have 4 populations, but I have 2 infected populations. One is normally symptomatic, the other one is severely symptomatic. So both of them, you know, can become recovered, and so, you know, susceptible population. This actually, this was somewhat in a sense here. This arrow shows the concern of the question which was given earlier about what if the viruses mutate again? Well, yeah, I mean, let's assume after you have recovered, assuming that you don't have immunity, I mean, you can become susceptible again. And so, so another kind of, virus of the same family can take you. In the models, I'm going to consider, so the basic standard compartmental models, they deal only with one population. So we have, here I have not put the so-called exposed population. It's not being here, it's basically tucked into the susceptible one. But I'm only, you can see here, I'm only hospitalizing the severely symptomatic. I'm also very interested in what is the effect of the limited number of hospital beds being available. Also, further, I'll be interested to see how the medical supplies, I have my capability to produce medical supplies, the medical supplies which I have already produced and stored, and the delivery, how they're actually going to have an effect of the whole on the whole system. So it's pretty much like basically 3 or 4 times multiplication of scaling 3 or 4 times what we saw with this bathtubs and valves with the software bugs. It's just some kind of, you can imagine that there will be some sort of connection like that here. Now this, I'm going to come to this plot again for, to explain what is going on. I'm going to demonstrate here how this is being solved. Actually, I'm going to bring a studio here. And so, first of all, I developed this package which is supposed to make this type of simulations convenient. What I'm going to show, actually, I didn't need to bring RStudio. Let me just show the dashboard here. So in this dashboard, we're going to see, maybe I should zoom out. Yeah. So, all right. So as I said, we're solving differential equations. This the systems of differential equations, and there's an omission here, I guess, on my side. Let me actually do make some sort of reference here. What is going on with the compartmental models I'm dealing with? We have this susceptible, infectious and recovered populations. We write differential equations like that. These numbers here, the contact rates, I was trying to, in a sense, give an idea what the contact rate is with the graphs I was showing earlier. And the graphs like, propagation through the city and so forth. And I'm using some more complicated models than that. I'm using, say, not SIR, but there's a SAIR model, which is, say, this one, which in which we also have an exposed person. The other thing is that I'm not having one infectious population, I'm having 2. So this model here, I'm going to have this equation here, which is feeds, this is for the exposed people and feeds the infected. I'm going to have it split up into 2 different equations. And so further, I want to extend these models to deal with hospitals, hospital beds, and medical supplies. So what we see here, it's actually one of these models with the 2 infected populations and has hospitalization. Let me see, hospitalized population, you can see it somewhere here. And I'm going to play a little bit, I guess, with the numbers here. So because we are trying to do some quarantine scenarios, so you can see these gray lines here, they tell me when the quarantine started and and when it finished. If I say extend the quarantine, the profile should be somewhat different. I mean, you can see how we flatten the curve, but say 100 days is way too much. So we're basically trying to figure out, all right, well, if we have 56 days, which is like, I don't know what, 7 weeks, no, 8 weeks, right? What is the right time to start to start the quarantine? And I can play with it a little bit, all right? So, I mean, you can see that actually there's some very nonlinear effects. These curves here, they were showing me the number of exposed, the number of infected, severely symptomatic and normally symptomatic. And so there's some very small range of starting the quarantine in which the effects can be actually quite dramatic. So this is what is happening here. Of course, we can ask ourselves what is going to happen if there is no quarantine. So I'm going to put quarantine length to 0. The quarantine started at 365 days, right? So this is how the thing looks if there is no quarantine. Now, if I have so if I actually do make my quarantine to start at day 70 and then be like certain now, say 60 days long, I mean, we see a very different way of how the infected, both normally symptomatic, severely symptomatic, again, are going to be evolve. So this interface here allows some other things to change, like we can change, say, contact rates and etc. Since we don't know the contact rates, the contact rate is an important parameter. It basically tells you how, I mean, obviously in this big village or campus or whatever I was talking about, it is an interesting question, how many people you meet per day. And these people, if you are infected and you meet these people, there's also a certain probability these people can contact the disease. Maybe they need to meet 5 infected people in one day in order to get infected and so forth. So this contact number is doing that. It's modeling that kind of that part. Anyway, this here, there's something else I wanted to mention. Since we are talking about hospitalization and etc., I'm going to remove all the populations and I'm going to pick only the hospitalized population. So you see, if I say plot the hospitalized population together with the severely symptomatic one, I mean, so yeah, you can see that this is my severely symptomatic, and let's actually, since I wanted to do a quarantine, actually, whatever, this, I guess you need to believe me here, and I'm going to remove the infected one. The hospitalized population is trying to have the profile of the infected one, but because there are a limited number of beds, hospital beds, that's why it's being cut off here. So in America, the number of beds per 1,000 people on average is 2.9. Some other countries have more. But then it's also, it's not just that straightforward. I mean, I have used 3 beds here, but obviously this some percentage of these hospital beds are already occupied. We're not going to remove, you know, existing patients just because, you know, some COVID-19 patients come in, say. So anyway, this is, so here, ideally, I should be able to see also both the effect of the quarantine is going to have also on the hospitalized population. Now, I don't, so yeah, you can see how the quarantine, whatever was the size here, it was flattening the curve, but then it started going up again. Again, this is the same, it's going to follow to a point, the same pattern as the severely symptomatic people. The thing is that the beds, they're not necessarily constant, right? So if I go back to this plot here, this number of beds here in the hospital, it can actually decrease. And there's a certain rate of the beds being changed per day. And this actually allows me to say model both the, say, if I'm not modeling this part here with the medical supplies, I can model the medical supplies not being sufficient and also medical personnel being sick and dropping out. It would be better, of course, if I make the medical personnel to be part of the populations here. But well, I mean, I decided I don't want to, or whatever, you know, for whatever purposes, you know, instead of like making two more populations for the medical personnel, I just want to have one adjusting rate, which actually tells me, you know, how available the hospital beds are. This also assumes that I can find relatively easily other medical personnel, right? So another thing here to consider is that maybe we can expand the hospitals or build new hospitals. I think this is, I read somewhere that China, this is what they did. They actually built 2 hospitals overnight in Hubei. And so this is, you know, what is happening. Now, back to the big picture here with the model making. And as I said, okay, fine. What I was showing you here is just gathering scenarios and doing some kind of playouts based on the quarantine. But what about calibration, right? So I'm going to, no. Whatever I did, sorry. This interface here, one of the reasons I wrote it with, this is obviously shiny, but this is actually Flex dashboard. And one of the reasons I did this with Flex dashboard is that it's relatively easy to change the Flex dashboards into something something else, right? Like say it is pretty straightforward. And so here, for example, you can see I started a particular model. I have put my sliders for the different contact rates and etc. for the quarantine parameters and etc. Now, what I want to do, I actually want to do calibration with some real data. So in this GitHub repository for this, which I'm using here, you can actually find this dashboard, which is called Hubei, and I have taken some Hubei data. Actually, it's one month old, but this is real data from Hubei. And what I did, I add a new slider here, which I'm going to explain. And I also, when I have this data here from Hubei, I actually plot it together with my solutions. So this was a little bit too much code demonstration, but let's just look into the dashboard, how it looks like. Ideally, it should be pretty obvious that I have real data here. So yeah, this is the data from Hubei. And so now the calibration. And the calibration, I mean, obviously I have a quarantine. So let's say, I mean, they did actually have a quarantine. So in effect, and somebody asked what is the effect of do I model the quarantine to be 100% effective? No, I don't. I can actually change the quarantine to be less effective. And you can see if I change the quarantine to be the contact rates to decrease not 4 times, which was before, but only at 71%, you can see the effect is becoming, it's not that good. You can actually, and alternatively, I can simulate total lockdown. And kind of, with the total lockdown, again, we actually really moved this type of this type of peaks, development further. So anyway, so here, but let's back to modeling for Hubei. Obviously, the way the data was collected, I mean, there's some incubation period and infectious period. So I see here this slide here tells me what I'm seeing here. What are the recovered? These are the recovered in purple. This purple line here, the recovered, and the infected ones in this bright blue. There's also deaths, but the deaths are too little, so you cannot see them here. So now what I'm trying to do, because I know that my I don't think I put the incubation period here, but again, because this is a Flex dashboard, I can actually easily do that. I'm going to move the data because I assume that say there's a certain, the incubation period is say 2 weeks, and then the infectious period is 30 days. I can actually try to see how and when, I can actually try to get this data closer to what I'm having. I have done this kind of manual calibrations. It can be done semi-manually. It can be done completely automated in an automated manner. It's not particularly easy, but this is actually the next thing we're trying to do after we have been doing, I mean, we have done some sort of modeling and we have developed some model. This is again, the picture I'm talking about here. We're gathering, different type of scenario playouts, and we're trying to attempt calibration. And especially with some, like how China was already having an experience with if we believe the data which we see from the different countries for the coronavirus, basically we can try to assume with the models we have, we actually try to see do we have models that fit the data from those countries, and see are these models operational for what we are going to try to do further. All right, so I actually have more discussion about that, but I'm going to stop here for questions, and let me see.
One of the questions was, why is there no lag effect with the quarantine?
There is no what effect?
No lag effect. Well,
there was. I mean, I thought it was obvious, actually, for that. So the quarantines, yeah, actually, I'm not just going to dismiss this question. If I sound dismissive, was not my goal. Actually, this is what I want to discuss next. And there's something called sensitivity analysis. So bear with me here. I'm going to bring up the sensitivity analysis. So actually here, like what I was trying to show you by putting sliders around, right? I mean, I can systematically run my models in such a way, like you can see here, I have staged some experiments for the quarantine starting between 50 days and 120 days. How well do you see this? Let me zoom. And so here these are basically, these contact rates, they're not just constant, they actually become piecewise functions. And I should have probably plotted the piecewise functions, but you can see here, if the time is between the quarantine starting date and the starting date plus the period 56 days, then the contact number changes to be 4 times smaller. This is what this is doing. It's like a simple piecewise function. So now with this number is fixed, the base rate for the contact rate and the quarantine length and the decrease of the quarantine. I'm actually running this for a range of quarantine starts, and I want to see how many, how the profiles are going to going to change. And as I said, like, I mean, if I understand the question correctly, we can see that there is a lag, right? So if I put the quarantine, for example, to be around, say, 50, right? I mean, we can see how this has been pushed forward, right? And so the other thing, I mean, I'm not sure what exactly lag means, but obviously this is not that, it's not that simple. The quarantine start is not the only determining factor. It's also the quarantine length. So this actually can be seen with, if we do 3-dimensional plots. And so let me, ideally I should try to convince you that this is doing that. So, all right, so here what I'm doing is, this is basically producing a certain type of parameters data frame, right? And so, you know, whatever they mean right now, but basically I can tell you right now, this is the quarantine lengths on the first column and the quarantine starts on the second column. And so here I'm actually running again a loop through all of this. Now you can see I have both variables being changed in this piecewise function. And then after that, I'm plotting the results. And so these 3-dimensional results, they can tell me, you know, how the whole thing developed. Now that's actually interesting. You see, I'm actually plotting here the death from the infected population. And the reason for this is that the way I'm accumulating the debt. So in a sense, I can easily, there's something called area under the curve. And the way I have formulated my equations, I'm actually using this area under the curve being tucked into the formulation of the equations. I'm looking for the model I'm using here. So let me find this model here. I'm going to show you the equations I'm using. So if I do this and if I do, all right, that was discouraging. All right, well, maybe just a moment. I'm going to I'm sure it's supposed to work. So I'm going to evaluate it and all right, yeah, fair enough. There is no, I guess I didn't load my package. So the package is this ECM mon is the package I'm going to be using. This here produced a model object, which I'm going to show. It's this model object has the stocks, the rates, and more importantly, has this right-hand function. So what I was saying is that if you look at the formulation of the deceased infected population, this is what this is here. You can see this is the derivative, and it's just the derivative is the number of people dying per day. So because these are differential equations, in a sense, I'm integrating it. So this is actually, so this DIP, you can look at how, you can see how it's different from the profiles of the other two populations here, the normally symptomatic and the severely symptomatic. This is already integrated. This is already area under the curve type of measure. And so when I do this kind of tests, you can see that I'm running my time horizon is 365 days, and I'm taking the last element from the solution here, and this is giving me the total number of deaths. So this is basically showing me what are the deaths with some kind of different combinations of quarantine starts and quarantine lengths. So I mean, this again, you know, presumably using plots like this, we're making some decisions where to go. But more importantly, when we do this kind of, and I'm just bringing up sensitivity analysis. Sensitivity analysis is very important when we develop this kind of models. As I said, some of the interdependencies are highly nonlinear. And because of this, first of all, we want to know if we model the situation correctly. What are the inherent kind of inherent dramatic effects which might happen at what ranges of the controlling variables. But I can also use sensitivity analysis to just verify that my model is working correctly. Like say, you know, I would expect certain things to happen, or something to be in effect by changing some of the parameters. So, all right, well, this was with using the so-called single site models. I think I probably discussed everything here I wanted to discuss, and I'm going to bravely mark all this here. So I do actually want to see if have any questions related to that. Next, we're discussing the multi-site extensions. So, and I'm sorry, I'm just going to, yeah, the question I see here, two questions from a user AD393. Shouldn't contact rate come close to the plateau if we assume non-essential worker population will largely comply? Very interesting, yes. Now, this is actually, the contact rates, where you might put any function, right? I mean, the way I was showing you here, I just put some piecewise function because it's easy to simulate. It's easy to simulate this. Let me bring up the piecewise functions right somewhere here. It's easy to show and explain the effects of the quarantines. You can put any function you want here. It can be, of course, learned from some past experience. Like say, you know, if you know if you have certain assumptions or certain policy in mind, you can, you know, program this function to behave in such a way. Or if you know how the contact rates developed, you know, in some other country or some other similar kind of disease, like say we had other SARS and MARS, you know, infectious diseases, like say a decade ago, you can actually put this kind of functions here and then see what are the effects. I hope I'm answering your question. What is your prediction for ending the quarantine in May 4th and in mass? Yeah, that's great. I don't live in Massachusetts, I'm sorry. You know, this might be, this is actually one of the things Rachel mentioned. You know, not everyone in this meetup today is from Boston or Boston area. I live in Orlando. I'm not sure, I'm much more concerned about, you know, modeling scenarios of New Yorkers going, you know, trying to migrate from New York and coming here to Florida, and what to do with that. So, what findings, if any, were surprising to you? That's very interesting. Well, unfortunately, with this model here, these models, they didn't surprise me that much, but some of the other models, they did. And since we're at the end of the meeting, I'm going to kind of bring up some stuff I did in Mathematica, because since it's about surprise, this was actually, there's some, as expected, there's some highly nonlinear effects of these models, right? So first of all, you can see more or less this is what I was doing here in this graph. And so far what I was showing you, I start with the basic susceptible, infected, recovered model, and then I extend it in a variety of ways. Here in this notebook, this is about the economical model. I was just showing you the behavior in these dashboards in R with Hubei and so forth. It was this this extension of the standard models with the hospitalization. Now in this, so the model I was showing earlier, in the last 10-15 minutes, was dealing only with two of these rectangles, the infected, the populations, and the hospitalization. Now this model here, what I'm showing is actually taking into account the medical supplies production. And so, so I'm going to skip whatever this here is. So yeah, so here you can see, like say, I mean, again, this is somewhat expected, how much the infected and the hospitalized are going to change if I change the supplies production rate. What you can see here when I'm making this simulation, I actually give quite a lot of hospital beds to this hospital. 100 beds per 1,000 people. This is at least 10 times than any kind of country, So anyway, now basically the hospital beds themselves are not a restriction, it's the supplies. But then I'm actually going and start to see what other effects these medical supplies have. And especially if I start to, I mean, like you can see here, if I have some kind of combined this medical supplies were delivered with certain period, like say once in a day or twice in a day, 0.5 means twice in a day, or they can be delivered twice in 3 days or something like that. And then I also have certain disruption. The disruption of the delivery process, I'm going to show the curve here, somewhere here. The disruption is say this, right? Everything looks normal, and then at some point the delivery gets slowed down by twice, right, or 80%. So combining the disruption and the and yeah, just a moment, going back down to this, combining the disruption and the delivery periods, right? I mean, I can see that there's some fairly non-linear effects here. This, by the way, this type of plots, this is not something you can deduce with any other method. Like say, I don't know, like say statistical methods, right? I mean, you need to actually sit down, scratch your head and figure out what is this, what exactly the process, where these non-linearities come. And so I did actually spend quite a lot of time trying to explain to myself or figure out, is this actually expected and so forth, right? All right, I'm not going to go for that. Like the multi-site extension, I think this is the most interesting one. And I'm actually going to try to speed things up here. So first of all, as I mentioned, everything I have been doing stuff both in R and Mathematica. The multi-site extension is an extremely interesting thing I want to implement in R, and I have done it to a point. What you are going to see here, and I apologize for this code, and I'm not sure what type of the audience cares, but you can see here, I have a mechanism of joining two models. Like each of these models produces, say, hospital, profile like this. So I know how to join two models. From these two models, I know, I mean, you can see if I put some initial conditions, I can actually make a common simulation for them. And now I can just go further and basically do this with, say, I have arbitrary amount of models I can join into one, and then do some simulations. Like say, for example, here I have 3 models, and you can see they have different IDs being associated and different results are being obtained. All right. So unfortunately, I didn't have time to finish this before this presentation. I didn't have time to finish this implementation, which actually includes the traveling patterns between the different sites. I'm extremely interested to model what is happening when I have different sites, from, like when I say sites, think about cities or some sort of aggregation. Let me bring this, bring a notebook here. So this is very close to what probably is going to be happening in reality, right? Like I'm going to be having some kind of, say, imagine this is some city like Orlando, Boston, whatever. These are some neighborhoods. These are some traveling patterns. Each of these arrows tells me there's some throughput, how many people from here go to here. I mean, you can see everybody goes to 12, but I guess nobody goes back to 7 or whatever, right? So this is just a random graph to test this. And I'm actually, yeah, I'm kind of making some simulations. What I was showing earlier is that if I do this with, say, a particular type of graph, I mean, I can, like, what I'm simulating here, I'm actually sending everyone from this node to basically go to this node, right, 84. So nobody's going backwards. All of the movement is in this direction. And so when I simulate my movement, with this multi-site extension, I want to see what I'm seeing here. It needs to make sense to me. On each of these sites, apparently I have this typical pattern I observe when I simulate with my standard modeling technique. And I want to plot what is happening on the first node and on the last node. You can see that in the first node, the total population is decreasing, and that's actually to be expected because nobody's traveling to node 1. Everybody's leaving it, right? And again, 84, the total population is increasing because it constantly gets people, coming in. Another thing I see here is that my population here, my first infected one infected person, it started in node 1. I mean, you can see the development here, it's much earlier than, say, this one here. So, all right. So this actually, as I said, brings some kind of confidence about the model. This wave we see here. So yeah, I'm going to play this animation. This wave here, we start with patient 0 and we see how it propagates. I mean, this is exactly what I would expect if my model is working correctly. So people are basically, they're traveling from between the nodes, and when they travel, they actually bring the infection, so to speak. The infection gets propagated as a wave in in this way. So this is the multi-site modeling, explained what it is, and I'm going to show how I'm doing this for US and say, and so doing this for US, right? It's actually quite a lot of things to be taken into account. Like, for example, I don't know this. Like, I'm covering US with certain sites like this, right? Like this, I'm covering US with this kind of cells. What you see here is a histogram, 3D histograms. All of the red points, they correspond to counties. The counties, I took the counties data from, let me show you. I took the counties data from this New York Times data. It's the New York Times data. And so basically I also have airport records, airport traveling patterns, and some other stuff like that. And so anyway, sorry, when I say this was not from New York, I know from the American government, the counties and the populations. What I know from the New York data is actually the number of infected people. So I can see here that, say, this is where New York is. I see 150,000. I'm not sure, do you see the hovering little square? It's like 150,823 people being infected. And so similarly, I have a similar map here for the death in New York area, 5,400 something, right? Anyway, back to this plot here. So I have partitioned US in this kind of cells. In each of these cells, I consider, that my classical models, the assumptions for my classical models hold. Now, that's a big assumption, right? But, and I'm trying to just make this computationally feasible for my experimentation purposes. So actually, I can decrease this computation to take less time. And so maybe I'll living dangerously here, but I'm going to actually try to demonstrate this. So I have chosen certain particular. Let me choose a somewhat less radius here. And so while is this evaluating, I'm going to be continuing talking about this here. So you can see the way I have aggregated the data, like say in that particular square. All right, so first of all, I mean, this should look more refined, right? So this refinement here, and yeah, when it comes, so I mean, we'll kind of discuss it, right? And hopefully my process didn't die. No, it just takes takes computationally, it takes a longer time when I have more refined grid. Now I can keep refining, right? But what I see here, for example, is that in this site, I have 18 million people, right? And so similarly, some others, you know, more or less, like this is Chicago area, New York, this is Miami, you know, Fort Lauderdale, so forth, right? This is what's probably San Francisco, I guess, you know, and so Seattle and so forth. And anyway, so we, with this, again, I actually assume a very certain type of density with this. I also know what are the number of the dead and the infected. And I have enough initial conditions for me to stage my computations. So what you see here, somewhere here, I should be setting up my initial conditions to correspond to the populations which I have, the total population, the population which is susceptible, the infected one. And now again, because if I believe the data which I have obtained, you know, and then I'm actually staging the simulation and try to see what's going on, you know, into the different sites. So more or less, this is it. This, by the way, does not include the traveling over the air because it's down to 5%. And basically, I'm already doing a quarantine scenario. Now, when I said that I'm more concerned, not so much concerned about Massachusetts 4th of May quarantine finishing, but more concerned with, say, you know, New Yorkers coming to Florida. I actually might decide to actually play out this scenario in these graphs I'm using to actually the underlying graph, which is being behind this, because obviously each of these cells connects to the others, right? The nearest neighbors. This is my graph right now, but I can make a particular path which actually simulates New Yorkers migrating to Florida and see what are the effects. So I think I'm, you know, more or less finished what I wanted to say. Let me just go here. Very important, and this is, I'm going to be very brief about it, and very important thing to discuss is what is the impact on the economy. And I'm actually there, I'm developing right now a separate economy model, which if I know what is my demographic of infected and dead, and if I know what kind of demographic people, what is the demographic of the people being involved in the different industries, I should be able to evaluate, or I hope I should be able to evaluate what is the outcome of this. US maintains a very nice data for how the different industries interact with each other. So in order to produce 1 unit of, say, utilities or whatever, construction or wood products, what is required from the other industries for this to happen, or the other way around, for, you know, how much these industries here, they contribute to the others. So this is the so-called input-output analysis. And so this input-output matrix, yeah, I advise you to kind of look into some of, at least the original, maybe I can show you this, yeah. So Scientific American, some time ago, I apologize. Some time ago, some Russian guy, naturalized American, he made this kind of, developed this technique of different industries, how they connect to each other. This is a publication in Scientific American quite a long time ago. After he developed this during the second or the first World War, I think, it was almost immediately embraced by US. So this kind of records are being well kept, and they used to make some kind of economic macro analysis. So back to this plot here. So what I'm saying is that doing some input-output analysis, doing the adequate epidemic modeling, I can actually try to see how the epidemic impacts the different demographics of the different type of industries. And from that, I can actually see, for example, how the whole economy is going to be impacted. Obviously, there's some other policies into effect. This kind of separation is very simplistic at this point. These models, they can be entwined, but at least initially they can be kept separated and see what are the effects. I didn't have time to finish this before the presentation, but I am a big fan of something called morphological analysis. And you can see here like some of the questions we have been discussing. Like I've been making a breakdown of the typical decision maker kind of questions, which are on this side, and the data and the algorithms which are being utilized, and kind of trying to kind of see with this paradigm, you know, what exactly I'm going to be, what kind of models and what kind of data I need to get in order to produce more adequate models. I think this is it, and I think you know, I mentioned everything. So I'm going to look into some of the, I mentioned everything I wanted to discuss in this presentation. So I'm going to look into the chat. So if there's any, Jared, is there any any way to manipulate your model based upon if specific demographics don't follow quarantine? Yes. I mean, it's compartmental models. You just do different compartments. Like, you know, for example, I'm only using two infectious populations, but say if you do this kind of model for when you try to do, say, vaccines, say for rotavirus, right? I mean, you know what your target age is children between 1 and 5. Because children from, you know, which are less than 1 year old, they have immunity, natural immunity from their mothers. The other ages, though, they still also get affected by rotavirus, but to much lesser degree. And so there's some models which have, like, say, you know, dozens of age groups, right? And so it depends also what is your time horizon. Like in this kind of model I'm discussing, imagine your time horizon is 50 years. Then actually you need to look for how people migrate between the different age groups. So anyway, students, I can actually use that. I can make them as a population, and this population to kind of know how exactly they change, or they kind of move from one group or compartment. This is the technical name, since we're discussing compartmental models, to another. This actually is it's actually a quite interesting question, which I do for recruiting modeling. And another thing which I want to mention, which is related to this, in this system dynamics GitHub. So there's this pet rituals dynamic. So it's very similar, but you see, like, for example, I mean, I'm in some sense, I am having this different populations, right? So I want to, not just for dogs, I want to imitate everything what's happening for all kinds of pets. Like dogs are very popular, cats, and also birds in US. And so now they also, you know, when you are, you know, one dog doesn't turn into a cat. So it's actually this model, if I make this model, I can make a very similar one for cats and just combine them. But basically this kind of dogless population, why they become, when they become people who want to have, when they do become dog owner wannabes. So this actually is usually people who finish, this is the reason I'm mentioning it in regard to this question. People who finish school, move out of their parents' house, you know, or millennials, you know, they think that having a pet before having a child is a good training experience and so forth, right? So anyway, this is actually related to that. And yeah, I mean, you just put the populations you want and you can model them. So I am not going to answer Jared's second question because I want to see some of the other questions.
There was a question up above about what package you're using to get the latest data. And so we shared a few examples in the chat, but thought it may be helpful to show you.
Yeah, right. In both Mathematica and R, I'm going directly to GitHub and downloading the data. I'm going to show you how I did this in this R notebooks, right? Oh, I bravely closed it because I thought, oh, well, let's see. Yeah, just a moment. So I don't want to do that. No, I don't want to do that. Anyway, yeah, basically just going directly to I'm just going directly to GitHub, say for New York data, right? And I'm taking from there what they have. And so the data curation and massaging is very important. That's why, for example, actually, let me go back to my GitHub here. That's why in my GitHub, I actually do maintain some of the, in this system modeling project, I do have the data I have worked with, right? Germany, Botswana, you know, whatever, right? This data, you probably, large part of the data you saw here, you can find it, you know, in this repository. The one for New York I'm talking about is, it can be found, I mean, I'm just going to bring this quickly. It's like, say, New York Times. So if you go to this markdown here, right, in the references, somewhere here, this should be, you know, these are like different data sources, right? So this is from New York Times. This is the data they maintain, they update it fairly often. And this is from Johns Hopkins Institute.
In the last minute here, I just wanted to ask if there are any other ways that people are working together, or hackathons that people are joining, or other communities where people can get together.
I've been invited. Well, I think everybody wants to make a hackathon in one point or the other. DevPost apparently is a popular enough hackathon. I was invited to a hackathon which was for Germany, probably like, say, yeah, if I go here, okay, unfortunately, it doesn't, I mean, yeah, well, the couple of hackathons I participated, I have to say, I didn't actively hunt for them. In this particular German hackathon, knowledge of German was a requirement. It's some of my friends or coworkers, they suggested that I should do that. At some point, actually, I stopped going to hackathons because I wanted to develop this R package for this presentation. So I don't know what is the hackathon landscape right now.
Mm-hmm. Well, just if there is anything that anyone from the group would want to share with each other, you can post that on the meetup group too. I know sometimes people will send me messages about things they'd like me to share with the group. And so I just put that in the chat. There's something called projectcovid.org.
Oh,
well.
Yeah, I'm sorry if you, Rachel, if this wasn't a question, this was more of an invitation to everyone. I just jumped in.
No, it's to you as well. So that's okay.
Great.
But if there are any other questions that we didn't get a chance to address, you can use them.
Somebody asked something very interesting here. Talk about Wolfram language. I don't know how much you want to know, but both I and Mathematica, or Wolfram language, they're both descendants of Lisp. And Lisp is a functional programming language. Right now, it's very functional programming paradigm becomes very prominent because turns out that certain, I don't know, parallel computations, some other things, you know, especially related to data science, pipelines, and etc., much easier to do with functional programming. I can talk a lot about the similarities and dissimilarities between Wolfram language and R, but what I want to reiterate what was mentioning earlier at the beginning of the presentation. If you know one of them, you can become relatively proficient in the other one. I do prefer R for a variety of reasons. One of the reasons you saw it, this was the Flex dashboard and Shiny and so forth, right? So Wolfram language, the models I showed, they're much easier. The type of modeling I was discussing, it's much easier to develop in Mathematica. There is no, to my knowledge, there is no other system which can do this kind of symbolic manipulations, also having a powerful numerical solver for which I can do this kind of computations. Like say here, I mean, I closed some of the notebooks I opened earlier, but say if I go back to this notebook I was showing earlier about the supplies, whatever, right? Supplies and hospitals and etc. So there are quite a lot of things happening here in the background. Like say, if I want to change one of these equations or these symbolic equations, I mean, I can do this relatively easily. NDSolve, which is the numerical solver of Mathematica, is, you know, it's actually quite powerful. It's very, very easily accessible here within, you know, within Mathematica. The one which corresponds, which I use in R, DSolve, it's actually absolutely great. It's written by some of the people who are very prominent and knowledgeable. I actually advise you to kind of, if you're interested, I mean, since this question was asked, it's a very good idea to know both both systems, how they actually can be used to solve differential equations. If I show you here, I mean, it's pretty straightforward actually in many ways, but I do have some sort of low-level examples here, which, let me see, this is a markdown. In these low-level examples, I mean, how I set up the solver, how I make the solutions, somewhere here, you know, it is explained to fairly well. This is the solver I'm talking about. In this solve though, it's actually is just more powerful by design. You know, it's because it utilizes the full-blown symbolic capabilities of Mathematica. So there's some things you just cannot, you know, you cannot do with just one package in R. All right, well, I think I talked too much about Wolfram language, I guess.
No, that's okay. But as I was just saying, if there are any other questions or anything we didn't get a chance to cover, I know we're a few minutes over here, but feel free to use the Meetup page to keep asking questions, and then Anton can answer there as well. But I'll also post the link to this recording as well. But thank you so much, Anton. That was great.
Oh yeah, thank you for
thank you for all your work and for all the preparation that went into that. We really appreciate it. And again, if anyone else is interested in speaking or would like to do a virtual meetup for next month, just let me know and feel free to reach out. Thank you all so much for joining.
Thank you. Yeah. Good luck, everyone. Bye.
Bye.